talk about Descartes' rules. For example, if you have some polynomial, p of x, and you look at the number or sign changes that you have, remember that's positive. From positive to negative, that's one sign change. From negative to negative, no sign change. Negative to negative, no sign change. We definitely have one positive real zero or root. If this number would have, say, been 4, you can have 4 or 2 less or 2 less. Why don't I go positive real zeros? Now, the number of real zeros is a non-negative number, non-negative whole number. You can either have 0 real zeros, or 1 real zero, or 2 real zeros, or 3 real zeros. You can't have 2.5 real zeros. You can't have -1 real zeros. That's why I stopped at 1. I meant to say 0, of course. If you have 1 and you take away 2, you'll be a -1. So I didn't go down from 1. So in this case, we definitely know this polynomial has one positive real zero. Guaranteed no matter what. Descartes' rule. Now, we just talked about positive real zeros. What about negative real zeros? Well, if you look at p of negative x, and then you find a number or sign changes, you can figure out how many positive real zeros. Excuse me, negative real zeros. Instead of x, we plug in negative x. We get negative x, and we cube it. We take away negative x and square it. We take away negative x, and then we take away 3. Well, this happens to be negative x cubed minus, well, negative x squared is x squared. The negative x is plus x minus 3. No sign changes, one sign change, or second sign change. So it has 2 or 0 negative real zeros. So for example, if you were using the rational root theorem test and you found the list of zeros from -3 and 1, once you found, say, a positive 0 that worked, don't look for any more, because Descartes' rule says you're only getting 1. So don't even bother looking for a second one. On the other hand, if from those possible rational zeros, you found 1 already, that's negative. You found the -1. Well, you don't have 0 then. You must have 2 negative real zeros. So there'll be another -1. The only thing is that, well, in this case it won't be, but in theory you don't know that other 0, because we only found 1. You don't really know that other 0 is rational. It could be irrational, but it won't be imaginary. Okay, so why don't we use this information about sign changes and number of positive and negative zeros to actually help us in a problem. Okay, suppose you're given this polynomial. Okay, suppose you're given the polynomial that p of x is 2x to the 4 plus 3x Excuse me, how about we look at this polynomial instead? Let's try that again. 2x to the 4th plus 15x cubed plus 31x squared plus 20x's plus 4. The first thing I notice is that all the terms are positive. There are no sign changes. So there are zero positive real zeros. So when I look at the irrational roots, I don't consider any positive ones. I don't check any positive ones because they won't work. There are exactly 0 positive real roots. If you wanted to test for negatives, well, if you raise negative x to the 4th power, nothing happens. If you raise negative x to the 3rd power, you'll get a sign change, so negative 15x cubed. Negative x squared is the same as x squared. Positive 20x times negative x will be negative 20x plus 4. Now this is a lot to invest, a lot of time to invest, to count the sign changes. But from the very beginning, in a matter of seconds, you can see, oops, no, 0 positive real zeros. There are no sign changes. Alternatively, when we plug in negative x, we have 1, 2, 3, 4 sign changes. So either there's 4, 2, or 0 negative real zeros. Okay. But mostly we know there are no positives. And personally, that's the only time I really use Descartes' rule, is when I can see really easily, oh, there's no sign changes, that means there's no positive zeros. But how would we go about finding the zeros? Well, rational zeros would always be of the form numbers that go into 4 divided by numbers that go into 2. 4 and 2. The numbers that I know of that go into 4 are these, I guess, 6 numbers. Plus minus 1, plus minus 2, plus minus 4. Numbers that go into 2 are plus minus 1, plus minus 2. So what are the possible rational zeros? Well, I'll take every one of these 6 numbers on top and I'll divide them by plus minus 1. That will just give me the top numbers. And then I'll take every top number and I'll divide it by plus or minus 2. So I get 1 divided by 2 is a half. But 2 divided by 2 I already have as plus 1. And positive 4 divided by 2 I already have as plus 2. In fact, the list is over. It's those 8 numbers. Those are the possible rational zeros, just from using the rational theorem test. But from Descartes' rule, we learned that there are no positive rational zeros. Combining, now all I'm doing is erasing the positives, so combining the results of both tests, now we know these zeros are negative 1, negative 2, negative 4, or negative a half. Those are the only possible rational zeros. Okay, so let us start checking them. Let's try negative 1. negative 1. And this goes into, I'm going to need more space for this. The possible rational zeros are negative 1, negative 2, negative 4, negative a half. Those are the possible rational zeros. So let me erase most of everything else. Okay, fine. So let us try negative 1. Negative 1. From the polynomial, the very top line, it has 2x to the 4th, 15x cubes, 31x squares, 20 x's, and 4 1's. Do synthetic division, you get 2. Multiplying these numbers down here by negative 1, all you can do is change the sign. So 2 becomes negative 2. I add, I get 13. It becomes negative 13. I add, I get 18. It becomes negative 18. I add, I get 2. It becomes negative 2. So what happened here? Does negative 1 work, first of all? 2, 33, 36. So negative 1 doesn't work. Excuse me. It becomes negative 2. And when you add, you get 2. Okay, so negative 1 was not a 0. So much for negative 1. Now, let's try negative 2. 2, 15, 31, 30, 20, and 4. I just copied down that line. Let's do synthetic division. We get 2. 2 times negative 2 is negative 4. 11 times negative 2 is negative 22. You add, you get 9. Multiply by negative 2, get negative 18. You add, you get 2. Multiply by 2, you get negative 4. And when you add, the remainder is 0. So we learned something. We learned that 2x to the 4th plus 15x cubed plus 31x squared plus 20x plus 4, this is equal to x minus this number right here, x minus negative 2, which becomes x plus 2, times this last row. It's 2x cubes plus 11x squares plus 9x's plus 2. Okay, now we want to factor that second bracket. X plus 2, the first factor, first bracket, x plus 2, is already factored. Now we want to try to factor the second bracket. Now, the list that we have down here, even though we made it shorter by realizing negative 1 didn't work, these may contain numbers that we don't need. That is, we can start with the second bracket as if it's a brand new problem. Find their possible zeros. Well, numbers that go into 2 are plus minus 1 and plus minus 2. And numbers that go into 2 are plus minus 1, plus minus 2. And if I take 1 and divide them by the numbers on the bottom, I get plus minus 1 and plus minus a half. If I now take 2 and I divide them by the numbers on the bottom, get 2 over 1 or 2 plus minus, and then I get 2 over 2, which is 1, which I already have. And remember, this here is exactly equal to this. But that never equals 0 when x is positive. So what we have are -1, -1/2, -2, and we've already discovered -1 doesn't work. So we have a shorter list. We don't have to worry about -4. So the two that we have to worry about are -2 and -1/2. I probably shouldn't say worry, but to test. Okay, right here, we are going to test, actually right here in our quote testing area, we are going to test -2. And we are testing it in this new factor. 2x cubed plus 11x squared plus 9x plus 2. We are checking good old -2. Like I said, it's 2x cubed, 11x squares, 9x's, and 2 is the constant. Now, yes, -2 already worked, but it may work again. It may work again. -2 times 2 is -4. You add, you get 7. You multiply and put it up there, you get -14. You add, you get -5. You multiply these two, it goes there, it's -10. Now, I may not know what 2 minus 10 is, but I know that only 2 take away 2 is 0. So this is not 0. It's -8, but it's not 0. So -2 does not work. Let's try -1/2. Now, does -1/2 have to work? And since there is one, well, there's no chance that there's 3 negative zeros. Does -1/2 have to work? Maybe not. Maybe not. So let's try it. It will work though. -1/2. You have 2x cubes, 11x squares, positive 9x's, constant is +2. -1/2 times 2 is -1. That becomes 10. -1/2 times 10 is -5. That becomes 4. -1/2 times 4 is -2. That's 0. So we learned something. We learned that this mess is the same as x plus 2 times x minus -1/2, x minus this number here, because that's a 0. And x minus it, namely x plus 1/2, must be a factor. And the other factor comes from here. 2x squared plus 10x plus 4. But now, I think you can see that 2 comes out of that. You can factor 2 from that. 2 times x plus 2 times x plus 1/2 times x squared plus 5x plus 2. And now, what you multiply, the order you multiply is up to you. I choose to multiply this 2 by the x plus 1/2. And then I'll get 2x plus 1, 2 times x, 2 times x is 2x, 2 times 1/2 is 1, and then times the rest. X plus 2 times x squared plus 5x plus 2. Okay, now we're going to put all our energy into finding out how to factor x squared plus 5x plus 2. But I wouldn't, okay, that's what we're going to put all our energy into. Okay, so far we know that either from the Descartes rule, we know that P of x either has 4, 2, or 0 negative real zeros. Either it has 4, or 2, or 0. Well, we know it doesn't have 0 because we already found 2 of them. So it can be 2 or it can be 4. And it's all going to depend upon x squared plus 5x plus 2. Let's find out when that equals 0. That's A in the quadratic formula, that's B, and C is positive 2. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now I plug in the values. It's negative b. b is 5. It's b squared minus 4ac over 2a. So it's negative 5 plus or minus that square root stuff over 2 times 1 is 2. Well, 5 squared, simple enough, it's 25. And 4 times 1 times 2 is 8. And 25 minus 8 is 17. So it's negative 5 plus or minus the square root of 17 over 2. Now, what if the instruction said, right? So we found the zeros. Here are 2 zeros right here. Remember, what's in that box is 2 numbers, one being negative 5 plus the square root of 17 over 2, and negative 5 minus the square root of 17 over 2. Those are 2 zeros, and from x plus 2, we got x plus 2 from knowing that negative 2 was a 0, and we get 2x plus 1, which was the same as, it came from 2 times x plus a half. Well, x plus a half is 0, and negative a half. So we found the 4 zeros. You have these 2 zeros. You have negative 2, and negative 1 half. Right here are the 4 zeros of p of x. And again, if the highest power of p of x is 4, you should find 4 zeros. They don't necessarily all have to be real numbers, but there are 4 zeros. And that pretty much completes the Descartes rule. Other than formally using it, because it's on an exam, the only time you might really use it to help you is when you want to find the zeros of a polynomial, and you can easily see that there's no sign changes. All the terms are negative or all of them are positive. In that case, there's no sign changes. That means there's no positive zeros. That real quickly, that cut out half of the zeros you need to look at when you list or consider the possible rational zeros. Because half of them are positive and half are negative. And maybe you can rule out all the positives. All right, good luck with it.